Hello and welcome. My name is Noah Deert, and this is Lesson 12, Maximum and Minimum Values of Functions in Two Variables for Portland Community College's Vector Calculus class, Math 254. In this lesson, we are going to be reviewing some ideas from minimums and maximums from single variable calculus. Then we're going to look at reviewing critical points of functions in a single variable. Then we'll finally get to doing local minimums and maximums for functions in two variables and critical points for functions in two variables. And then we will look at finding an absolute minimum or maximum for a function and how we can use that to optimize a function, or if we have a story problem, an application, and we want to be able to find where something is maximum or minimum, then we can do that for that situation. Let's go ahead and jump in here. So section 12.1, review minimums and maximums in single variable calculus. Recall from single variable calculus that the definition of a local maximum or a local minimum is the following. Definition 12.1.1. Given a function y equals f of x with the domain d sub f, then y1 equals f of x1 is a local maximum if there exists an open interval a to b in the domain of f where x1 is between a and b, such that y1 is greater than or equal to f of x for all x in the interval a comma b. Moreover, y2 equals f of x2 is a local minimum if there exists an open interval c to d in the domain of f, with x2 being between c and d, strictly between them, such that y2 is less than or equal to f of x for all x in the interval c comma d. This is very formal in how I'm writing this, but it's actually really important in how we do this. We need to be careful in defining a local minimum. So if I have some, let's give me an x-axis here. So if I have some line going up here, I need to make sure that this point couldn't be defined as a local minimum, right? So I couldn't just look at an interval. I couldn't have a closed interval right here that contains the point. This clearly contains the point. It's right there on the end. And in this, it looks like that is giving us a local maximum, and that's not okay. So we need to make sure that we have our point and that we put it between an interval. And here we see if we try and put this point in an open interval, no matter how close these get to the point, this is not going to be the greatest, this is not going to have the greatest y value within that interval. So when we do this, this rules out us having an endpoint for a local minimum or maximum. So if I have something like this, and we look here, this can't be considered a local maximum because I can't put an open interval that is inside the domain of the function around that point. So this is not going to work. So what we're saying is, if I have a point and I can put an open interval around this point, so here's a and b, then the y value of this point, so this is x1, y1, then this y1 is the maximum. It's a local maximum because it is the largest y value of f of x within this open interval. Now, we're not saying that it's the largest y value on f of x, because this function could come up and have higher y values over here, but if I can create a space where that happens, where it's the highest y value in that open interval, then we win, and symmetrically for local minimums. Okay. So essentially this is saying that a point on the graph of f has a y value that is a local maximum if there are points immediately to both sides of it whose y values are less than or equal to the y value in question. This is actually important. So we can have this situation where, so say I've got my x-axis here, and I have a function and it flattens out and goes up again. This y value that we have in this entire section, this is a local maximum, and it occurs on this entire interval. So it can, if we're looking on both sides, it can be that we have equal value on one or both sides. So to be a maximum, we don't have to have the points be specifically lower on both sides. They could just be equal. And this works because if I just ignore everything else, if I'm just zooming in right on this section, the reason this makes sense is because if I zoom right in on this section, I say, within this section, not looking anywhere else on the graph, what is the highest y value? Well, it is this y1. If I say, what's the lowest y value? It is still y1. So if I have a flat section, if I have a horizontal line on a graph anywhere, then within that region that it's horizontal, that will be both a local maximum and a local minimum. If we say regionally, then regionally, on that flat line, that the y value of that flat line is both the highest and the lowest y value on that flat line. So, all right, keep reading here. And f has a y value that is a local minimum if there are points immediately to both sides of it whose y values are less than or equal to the y value in question. This, did I write that right? That's totally a copy-paste error. I will fix that. Let me start back over. F has a y value that is a local minimum if there are points immediately to both sides of it whose y values are greater than or equal to the y value in question. This excludes endpoints from having their y values be local maximums or minimums. And I'm saying that in highlighted text because endpoints can be absolute maximums or minimums. So if we look at absolute maximums and minimums, again, for functions in a single variable, we have the definition 12.1.2, which says, given a function y equals f of x with the domain d of f, d for f, then y1 is the absolute maximum if y1 is greater than or equal to f of x for all x in the domain of the function. Similarly, y2 is the absolute minimum if y2 is less than or equal to f of x for all x in the domain. So note that the absolute maximum and absolute minimum may occur at endpoints. I should really say they aren't at points. They can occur at endpoints. I think that'll be clear why that is as we look at this following example. So example 12.1.1, I wanted to say one other thing. So remember that the absolute maximum is a y value. It's not a point. It's the largest output that the function can have. If I think about what's the range of the function, then whatever the largest y value is in the range, then that is the absolute maximum of the function. It's not the point, it's just the highest output of the function. Okay, so example 12.1.1. Take the function y equals f of x, shown in figure 12.1.1 below. What are the local and absolute maximums and minimums, and where do they occur? So pulling this graph up in GeoGebra so we can see it a little bit better. Here, this point at the bottom, this has a y value of -4, and this is the lowest y value on this entire function. At the far right endpoint here, the point 5, 6, this has a y value of 6, and this is the largest y value. 6 is the largest y value that this function outputs. So -4 is the absolute minimum, and 6 is the absolute maximum. -4 occurs when x is 4. 6 occurs when x is 5. So we'll go ahead and write that for our absolutes real quick before we talk about locals. So the absolute max, this equals 6, and it occurs at x equals 5, and the absolute min, this equals -4, and it occurs at x equals 4. So I'm not writing points here. Again, it's really important that we think of when we're defining a function so that we can talk about some application. So given an input of time and then an output of, say, distance from something, we want to say what's the farthest that our object ever gets from some starting point, then the distance is our absolute maximum, and it occurs at a certain time. It's not the point altogether. If I say what is the highest elevation on the planet, then if I say the top of Mount Everest, I'm not really saying what the elevation is. I said where that highest elevation occurs, but the elevation itself is the absolute maximum elevation on the planet. So the language is important in how we say this and not using points in this situation. So let's go back and let's talk about local minimums. Let's write this real quick. Local mins. So we're going to do these one at a time. As I look at this graph, I see that I cannot use this endpoint because I can't draw an open interval around this point here. If I attempt to, then we don't have anything on the left, so we haven't really created an open interval that is within the domain of the function that contains this point. And really, as I was saying before, we don't want to be able to have an endpoint because that would allow us to think of any point as a local max or min, and that's conceptually not what we want to be doing here. However, on this flat line, if I draw an open interval starting right here at this endpoint and right here at this endpoint, then I see that we get this y value of -2 along this entire stretch. And so within just this window, then -2 is both the local min and the local maximum. So let's write that down here. Where's my... Here we go. Is this not... There we go. All right, so we have a local minimum of -2. Oh, and this occurred on this stretch from when x is, zoom in here so we can see this, x is -2 to x is 0. And when x is -2, we do have that y value. When x is 0, we do have that y value. So the -2 occurs on that, but the way that we're going to call it a local min is that at -2, if I tried to draw, that's right, I'm using the screen draw from my video recording, and it works a little bit different than my PDF app that I use for drawing on. But if I try and put an open interval around this endpoint, then I don't get that this is a local minimum. So at -2, I do not consider this a local minimum, but if I draw over here, then we see that, yes, this is the lowest y value within this interval, and this does happen when x is 0. So we can say that -2 is a local minimum at 0, but we cannot say that -2 is a local minimum at -2. So as I want to go ahead and say where this occurs, I say that we have a local minimum of -2. I don't want to say at, I want to say on the interval -2 to 0, not including -2, but including 0. And I'll give some room, local maximum. -2 is also a local maximum, and here it's a local maximum on -2 to 0, and this time we're going to include -2 and exclude 0. And that again occurs because as I, oops, why is that doing a box? Clicked on the wrong marker. There we go. So as I look at this, the -2 is the maximum y value around when x is -2. But when I look around x is 0, the -2 is not the largest y value when I try and put an open interval around this. So let's see here. So that's why we have the local max at of -2 on this interval where we include -2 but exclude 0. Okay, going back to our picture here, we see we have local minimums of -2 that also occur when x is 1 and 2. So we'll just add those into our list here. And at x equals 1 and x equals 2. We also have a local minimum of -4 when x is 4. So an absolute minimum can also be a local minimum, but we're going to see that the absolute maximum is not a local maximum because that's occurring at an endpoint. So if we go back and look at, so there's no other local minimums here, but there are local maximums still. We have 2 that occurs at 0.5 and 1.5. Let's list that out. Oops. And then we have a local maximum of 4 when x is 3, and then 6 is not a local maximum, so that's our last one, 4 when x is 3. All right, so that's just a nice review of our single variable calculus look at absolute maximums and local minimums. We now want to look at single variable calculus critical points, so that we can remember how we found these given a symbolic function, or rather a function given in symbolic form. I'm being precise in how I say this. So section 12.1.1, critical points of functions in one variable. As we review local maximum and minimum values of functions in one variable, let us note again that these values can only occur when their corresponding input value, normally x, is a critical number. So why is that? Well, let's remember what the definition is. Definition 12.1.3, given a function y equals f of x with the domain D for f, then x1 in the domain of f is a critical number of f if either f prime of x1 equals 0 or if f prime of x1 is undefined. Note that within this we already said that x1 is in the domain of the original function, but now we're saying that it's not in the domain of the derivative, and that would cause a critical. So the reason that this is where we could get our local maximums and minimums is because if I have a maximum, then it's either, I'll just talk about this for maximums, and it's all symmetrical if we're talking about minimums. So if I have this y value at the top of this hill that is a maximum value, then the slope here is 0. If I have a sharp point, come on, catch up, processor, like this, then the derivative is undefined. But, so here I have x1. So x1 is in the domain of the function because that point does exist on the function, but the derivative is undefined because we have no undefined slope at a sharp point. So these are the only ways that we could possibly get a maximum, is if one of these, actually, I'm lying, we just talked about it. We could have a flat section, right? So, but again, if I have a flat section and I call the y value along this interval a local maximum, that's okay. That this, we are getting a critical value of 0, or a derivative value of 0 in this entire section, so we would have critical numbers along this entire interval as well. And there's no other way for us to possibly have a local maximum or minimum. So not every critical number will yield a local or maximum or minimum, though, and that is because if I set the derivative equal to 0 and find what x values that gives me, we could note that a saddle section here, it's flat at this single point, but this is not a local max or min. The points on the right are above, the points on the left are below. So we are getting that the derivative equals 0 at this point where for x1, but this is not a local max or min. So we have the second derivative test for single variable calculus. This says, well, this is going to allow us to tell if a critical number is a local maximum or a local minimum, or if it's a saddle point. So our theorem 12.1.1 says, supposing x1 is a critical number of a function f and x1 is in the domain of f prime, so it's not a sharp point that we're looking at, and f double prime, if x1 is in the domain of f prime and in the domain of f double prime, so we're not dealing with a sharp point on f or f prime, and so we can even do this second derivative test. If f double prime is undefined, then these little items that we have here wouldn't apply. So if f double prime of x1 is greater than 0, then f of x1 is a local minimum. And that's saying that we're concave up, right? If the second derivative is greater than 0, at this point we must be concave up around this point. If we have the second derivative is less than 0, we are concave down. And so we have a local maximum. If the second derivative equals 0, that means, so already the first derivative equals 0, so we know we're flat there, and the second derivative equaling 0 means that we have an inflection point where we go from concave down to concave up, or we go from concave up to concave down. So this second derivative test is a nice quick way of telling, once we get our critical numbers, whether or not that critical is going to give us a local max or a local min. So if we move to the next idea for absolute maximums or minimums, so if we're given a function or a story problem and we're trying to find the absolutely largest output or the absolutely smallest output, minimum output, then that can happen at a local max, a local min, but it could also happen at an endpoint. So in practice, we're going to find, if we're looking for the absolute minimum or absolute maximum of a function, we're going to find all the critical numbers, and we're going to plug all of these into the function, and we're going to plug the endpoints of the interval into the function. We're going to get the y values for all of them, and then determine what's going to be our highest or lowest values. So we're actually not going to use the second derivative test in this example right here, but we will use it, or an analogous version of it, in the two-dimensional situation, so that we can kind of define whether or not we have a local max, a local min, or a saddle point in a function in two variables, so that we have a surface in 3 dimensions. Okay, let's look at example 12.1.2. Given f of x equals 2x cubed minus 15x squared plus 24x plus 7, find the absolute minimum and absolute maximum on the interval 0 to 6, closed interval 0 to 6. So I'm going to get the derivative. I get 6x squared minus 30x plus 24. I'm going to set this equal to 0. And I'm going to divide by 6. X squared minus 5x plus 4 equals 0. Factor this as x minus 4, x minus 1. So x equals 4 or x equals 1 are both critical numbers for the function. Note that the domain of f is all real numbers, and the domain of f prime is all real numbers. So there's no critical numbers due to there's no sharp points here, because the derivative is defined everywhere that the original function is defined. So now that I've got my critical values, I can find my absolute minimum and absolute maximum by simply saying, okay, what's f of 0, by plugging in my endpoint, and that is 7. And then I'll say, what's f of 1, my first critical number, and I'm going to get 2 minus 15 plus 24 plus 7. That equals 31, 32, 33, minus 15 is 18. And then f of 4. This will be a little bit more fun to calculate. So 2 times 4 cubed is 64, times 2 is 128, minus 4 squared is 16 times 15. I'm going to think 15. Not 160 and 80 is 240. There we go. Plus 24 times 4, 48, 96, plus 7. So here we've got 128, 135, 141, 231, minus 240 is negative 9. And then f of 6. This is even more fun to calculate. 6 cubed is 216, times 2 is 432. 6 squared, 36 times 15 times... I'll show you guys how I'm doing this in my head real quick. Oops. If I'm doing 15 times 36, this is 10 times 36 plus 5 times 36 is 360 plus half of that is 180. So that's 460 and 540. So this is the mental math that I would do in order to hash that out. That I lost something, didn't I? 6 cubed is 216 times 2 is 432 minus 540 plus 24 times 6 is 120 and 24 is 144 plus 7. This equals, my difference here is 108, negative 108. 108 to 144 is 36 plus 7. 36 plus 7 is 43. And there we go. So we actually do get an absolute maximum at this right end. So the absolute minimum is negative 9 at x equals 4. And the absolute maximum is 43 at x equals 6 on that endpoint. Let's go ahead and pull up a graph and just confirm our results here. So I went and typed it in already. I've got these points. I want to change their labels. If I go to settings, I can say value here, and same thing on this. Settings, value. So we see on this function the absolute minimum occurs down here. Oh, that's really nice. The extremum is at 4, and the absolute minimum is negative 9. And then we see our absolute maximum on this interval is 43 when x is 6. So cool. No arithmetic mistakes there. I'm happy with that. Alright, now that we've covered a review of single variable calculus, hopefully you guys found that a good refresher. Let's now start looking at functions in 2 variables. So section 12.2, local minimum and maximum values. Now for functions in 2 variables. Local minimums and maximums of functions in 2 variables are analogous to local minimums and maximums of functions in 1 variable. Local maximum is a z-value on the graph of the function that is the highest z-value within some localized region of the graph, and a local minimum is similarly a z-value which is the lowest within some localized region. We're going to take a look at an example here in just a moment to see exactly what I'm saying. Definition 12.2.1, given a function z equals f of x comma y with domain d for f, then z1 equals f of x1, y1 is a local maximum if there exists an open disk d that's within the domain of the function where x1, y1, the point x1, y1 is also in this disk, such that z1 is greater than or equal to f of x comma y for all points x, y in the open disk D. Moreover, z2 equals f of x2 comma y2 is a local minimum if there exists an open disk D in the domain of f with x2, y2 in this disk, such that z2 is less than or equal to f of x comma y for all x comma y in this open disk. So note, since these local extrema, maximums, and minimums have to occur on an open disk, they cannot occur on an edge of a closed domain. So I couldn't draw, so say I've got some surface here and we close off some section of it, then the points on this edge we could not consider local extremum. They may be we may get an absolute extremum on an edge, but we're not going to get a local extremum. And this is for similar reasons for what we saw in our single variable calculus. If I am on, say, a hill like this, I don't want to be able to just say this point right here is giving me a local maximum, right? And we would be able to do that if I could just close a disk around just this section, and then we would say, oh, I can call this a local maximum now. But that's not what we want to have happen. So we don't want to have a closed boundary. We need an open disk that we're looking at. So if I have the top of some hill, I can put an open disk around that point and see that within that disk, that is the highest z value that occurs within that open disk region. So given a function in a single variable, we also have what's called a saddle point, which is mentioned in theorem 12.1.1. This is where the function is concave up on one side of the point and concave down on the other. And we are going to have, so here we have a saddle point flat right at that point, but it's concave up over here, concave down on the other side. We have something similar happen. We can actually see it in the graph right down in the bottom corner. So if I have like a hill on one side, on two sides, but downhill on the in other two directions, then that's going to be a saddle point for a function in two variables. So if you're standing on a hill or standing inside of like a little valley, but you could walk downhill going in at least one direction, you could go uphill in another direction, but at the point you're standing on, you're actually at a level surface, then you're at a saddle point. So it's not a local max or a local min. But it's also just not on the slope where it's all uphill or downhill in those different directions. It's not like just being on the side of a hill and saying, oh, it's just all uphill if we're going in this direction. Like here, this saddle point, if we're at the bottom of this valley here, but at the top of this hill at the same time, then we could think of it as a local minimum in this left-right direction, but a local maximum in the y direction. Okay, so when dealing with a function in two variables, the same thing can occur where we could get a flat spot on the graph where the tangent plane is a constant z value, so its slope in all directions is 0, that is neither a local maximum nor a local minimum. As with our single variable situation, this occurs where the function slopes down from this point in some directions and slopes up from this point in other directions. Example 12.2.1, given the function z equals f of x comma y, given in the graph shown below, determine the local extrema and the saddle points. So let me get this graph. Here we go. So we see a hill on one side and then this little valley-like area on the right side, and then at the middle of this valley, at the bottom of this valley, then you could actually slope down in the y direction and get more downhill. So it's actually the top of a hill if we were moving in the y direction, but the bottom of the hill if we're moving in the x direction. So there we have a saddle point whose y value is negative 575 over 54, and it occurs when x is 5/3 and y is 5/6. Over on the left, we have the top of a hill. We have a point on the top of the hill whose z value is 14, the x value is negative 2, and the y value is negative 1. So I can say that I have a local maximum of 14 when x is negative 2 and y is negative 1. So that's what we want to say here. So we have the local max is 14, and this occurs at, I think I said, what did I say, negative 2, negative 1, right? Yep. So it occurs at that point. And then we have a saddle point. I don't think of this as a extreme, it's not like the highest y value or the lowest y value or the highest z value or the lowest z value. Oh, speaking of which, I just found another typo. That should be a z. So I don't say like the z value and then at this point I'm just going to say the full point. So the saddle point is occurring when x was 5/3, right? X is 5/3, y is 5/6. and z is negative 575 over 54. And that's it. Okay, so let's now look at how we can find these given a function defined symbolically. All right, section 12.3, critical points of functions in two variables. Before we look at how to tell if a critical point in a two-variable function will yield a local minimum, maximum, or saddle point, we're going to do some review on Taylor series expansion for a function which is smooth and continuous near x equals a, so we're in a single variable, yes. And this is going to kind of lead into the whole explanation of how to tell. We essentially want a second derivative test to tell if something's a minimum or a maximum or a saddle, but it's going to be a little bit more complicated. Actually, it's going to be quite a bit more complicated as we look at this in two variables. So we're going to kind of build up to this whole classification of minimums, maximums, and saddle points for functions in two variables. And the definition of a critical point for a function in two variables is going to come after we do this little explanation of Taylor series again. So given a function f of x, if it's a nice smooth function, then it has a Taylor series expansion. So if it's smooth and continuous near x equals a, it has a Taylor series expansion for around x equals a. That Taylor series expansion is f of x equals f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared plus etc. This is for x values near x equals a. Thus, if we want to move by h, we get f of x plus h is approximately f of a plus f prime of a times h plus f double prime of a over 2 times h. And this is using the second order Taylor approximation. And so for our second derivative test, we really want to be thinking about second order Taylor approximations. And we're going to be using the same kind of thing except for in a higher dimension below. So, oh, I typed that out. Hey, look at this. I'm on top of it in the same way both times. So similarly, given a function in two variables, if we move by h in the x direction and k in the y direction from point a comma b, we use the directional derivative with u, the vector u equals h comma k, to get the second order Taylor approximation. F of a plus h comma b plus k is approximately f of a comma b plus the directional vector of u, the directional derivative in the direction of the vector u of f of a comma b being my initial point, right, a, b, plus the second directional derivative in the direction of u of f of a comma b over 2. So this is just analogous to what we had above, except for instead of just plugging in an x value of a, we're plugging in a point a comma b in for my second derivative and first derivative. The h that we have in my Taylor approximation for the single variable is actually going to show up in our derivative here in the next line. So when we take our derivative in the direction of u, we're going to see that this equals f of a comma b, that's just the same, this is coming straight down, plus the derivative of f of a comma b in the direction of u, well, that equals h times the partial derivative of f with respect to x evaluated at a comma b plus k times the partial derivative of f with respect to y of a comma b. So this all goes here. And then if I want the second derivative in the direction of u of f at the point a comma b, then this, we're going to take the derivative of what we already have here, where h and k are constant. So let's see, we're doing the derivative in the direction of u of h f sub x of at a comma b plus k f sub y at a comma b. Well, this is going to equal h times, actually, sorry, I'll write this, h times the partial derivative with respect to x of all of this plus k times the partial derivative with respect to y of all of this. So when we do that, we see that we get that this second bit here is all from this derivative. And so the h that we saw in my single variable calculus version, that is essentially this h and this k being multiplied by the partial derivatives in my two variable function version of this. So we're going to use this here in just a second. So a critical point of a function f of x comma y is defined to be when the partial derivative with respect to x and the partial derivative with respect to y are both 0. So when we're looking for critical points, we just find the partial derivative of f with respect to x, find the partial derivative of f with respect to y, set both of those equal to 0, and find any points that make both of those 0. So we'll see that in an example below. So any point that satisfies this is going to be called a critical point of f. If we plug this into the equation that we just worked out, so if we assume a comma b is a critical point, then both of the partial derivatives are going to be 0, but the second derivatives like f sub xx and f sub xy are not going to be 0 necessarily. So we plug those in for f sub x and f sub y, and we plug in 0 for f sub x and f sub y, and those will disappear. So we're going to get up here that this equals f of a comma b plus h squared over 2 f sub xx of a comma b plus hk f sub xy of a comma b. Oh, I'm also using in this that since this is a smooth function, since both of these derivatives exist and everything, that f of f sub xy equals f sub yx, which we'd done when we were doing partial derivatives. We'd seen that that's true for nice smooth functions. Oops, should be a plus k squared over 2 f sub y at ab. And then if I want my change in z, right, because that's what this is all about. We want to know, is the change in z positive, or is it negative, or is it sometimes positive, sometimes negative, at this specific point where my tangent plane is just a constant z value, right? So if we have essentially a slope of 0 in all directions, what's my change in z in different directions? Is it always up, always down, or always positive, always negative, or is it sometimes positive, sometimes negative? So my change in z equals f of a plus h comma b plus k. This is my new z value minus my original z value, f of a comma b. So I just take away the f of a comma b from this bit up here. And so this is approximately h squared over 2 times f sub xx plus hk f sub xy plus k squared over 2 times f sub yy. And again, this is an approximation because we just used the second order Taylor approximation for this. We didn't use the entire infinite expansion, but this should give us good approximations for small enough h and k, and it should allow us to get an infinitesimal dz if we let h and k both go to 0. So this next line, so we're going to start to classify this. We want to be able to work this equation in a way to be able to tell if my change in z is positive or negative. So for hk small enough, f of a f of a plus h comma b plus k minus f of a comma b, we say equals h squared over 2 parentheses f sub xx plus 2 k over h f sub xy plus k squared over h squared f sub yy. Essentially, we just factored out an h squared over 2 here. We say equals for hk small enough, meaning that we're essentially letting the limit as h and k go to 0. So notice this has a characteristic of quadratic in form. For example, if I had the quadratic q of w equals aw squared plus 2bw plus c, this changes signs when it has two distinct roots. So it'll have two distinct roots when b squared minus ac is greater than 0. I want to kind of show you where this is coming from. If I set q of w equal to 0, this happens using the quadratic formula at negative 2b plus or minus the square root of 2b squared minus 4ac all over 2a. And this has two solutions. So here I can factor out a 4 and then take its square root. So we get negative 2b plus or minus 2 root b squared minus ac. So this has two solutions when b squared is less than 8, or b squared minus ac is greater than 0. It has one solution when b squared equals ac, and it has no solutions if b squared is smaller than a times c. Right? So if this is negatives inside my square root. So if we have two solutions, that means, let me back up here. So if b squared minus ac is greater than 0, then there's two solutions to this quadratic. Now, if I'm looking here, we actually want to think of this in the following way. We want to think of this as f sub yy times k over h quantity squared, and this is like my w, plus 2f sub xy times k over h plus f sub xx. So we're thinking of k over h as my variable, because that's allowing us to say which direction we're moving in, right? So that's really my variable that's not changing, that we're not thinking about. We're thinking about the coefficients of the variables for this quadratic. So if in our case, let's just write this out. So if we want this to equal 0, then we would have negative 2f sub xy plus or minus the square root of 4f sub xy squared minus 4f sub yy f sub xx all over 2 times f sub yy. So we then have multiple, so the change in z equals 0 twice, meaning there are two values for k over h. Where the change in z equals 0 when this discriminant here if it's greater than 0, that means that in one direction f is increasing, and in another direction f is decreasing, right? Our change in z is positive some places, negative in others, so we must have a saddle point. So we see that expression again here. On the other hand, if we have f of xy squared minus f of yy times f sub xx is less than or equal to 0, then it must be that we only have either one solution or no solutions to this. So our change in z, that we're not going to have a change in z. If it equals 0, then the change in z is never switching from positive to negative. It just hits 0 for just a moment. So if our change in z, f of a plus h comma b plus k minus f of a comma b is greater than 0, this happens when my second derivative with respect to x, second partial derivative with respect to x of f is greater than 0, and the second partial derivative with respect to y of f is also greater than 0. So if we have no change in z, so this f sub xy quantity squared minus f sub yy times f sub xx is less than or equal to 0, and the second partial derivatives are both positive, then we must have a minimum, right? So this tells us that we're not going to have a switch, and these tell us that we're positive in both the x and y directions, concave up in both the x and y directions, so we must have a local minimum. On the other hand, the change in z is less than or equal to 0 when the second partial derivatives with respect to x and y are both negative. So we have concave down situations in the x and y directions, and we know that there's no change in z. So between the x and y directions, we couldn't have it suddenly switch and cause a saddle thing to occur, right? So we can summarize all of this, and really the summary is what we're going to be using, that we have a saddle point if f sub xy quantity squared minus f sub xx times f sub yy is greater than 0. On the other hand, if we're going to have a local min if f sub xy quantity squared minus f sub xx times f sub yy is less than or equal to 0, when f sub xx is greater than 0 and f sub yy is greater than 0. We'll have a local max if f sub xy quantity squared minus f sub xx times f sub yy is less than or equal to 0, and f sub xx is less than 0 and f sub yy is less than 0. Now if we have f sub xx or f sub xy or f sub yy equals 0, then these arguments don't work, so we may have to come up with a different approach. But I believe that the examples that we have here, we're not going to have to do that. So let's look at this following example. We want to find and classify the critical points of f of x comma y equals x squared minus y squared. And really, the whole argument I just gave for proving that we can classify our critical points in this way is not as important as being able to, for our practice now, isn't as important as just being able to use these formulas. So let's not get too caught up in all of the details that we just went through and really try and focus in on now understanding these formulas well enough to put them to practice. So if I'm going to classify the critical points of this function, I'd better find the critical points. So the critical points occur when f sub x, which equals 2x, and f sub y, which equals negative 2y, when these both equal 0. So 2x equals 0 when x equals 0, and negative 2y equals 0 when y equals 0. So we have a critical at the origin, 0, 0. So if I want to determine if 0, 0 is going to give me a saddle point, a local min, or a local max, we're now going to need the second partial derivative. So f sub xx, this equals 2. F sub xy equals 0. And f sub yy, this equals negative 2. So if I look at f sub xy squared minus f sub xx times f sub yy, this equals 0 minus a negative 4, so plus 4 equals 4. So we're seeing this is greater than 0, so we have a saddle point. 0, 0. Okay, so is that so bad? I mean, we may need to look at a little bit more if we're talking about a local min or local max, but really find your critical values and then find the value of this little formula, see if it's positive or negative. If it's positive, you have a saddle point. If it's negative, then check and see and look and see if the second partial derivatives are positive, both positive or both negative. All right, so go ahead and look at exercise 12.3.1 and use those classifications to determine to find and classify stationary points for f of x comma y equals x to the third plus 3y squared minus x squared y minus y cubed. And stationary points are same thing as critical points. So just another word. It's stationary, meaning that the derivatives are 0. So we're not going uphill or downhill at that specific point. Our outputs aren't increasing or decreasing. So this is an exercise for you, so go ahead and give this a shot. I will work through the solution with you in just a few moments. And we're back. So there's a lot going on in this one, and I'm going to run us through it. I'm mostly concerned with you following the strategy for how to find if these are saddle points or minimums or maximums. I know there's a lot of details that goes into this, but we don't want to lose track of the big picture as we're going through all of the tedious steps along the way. So I find the partial derivatives with respect to x and y respectively. F sub x equals 3x squared minus 2xy. F sub y equals 6y minus x squared minus 3y squared. I set the partial derivatives equal to 0, so 0 equals x times parentheses 3x minus 2y, close parentheses. This gives me that x equals 0 or y equals 3 halves x. For the partial derivative with respect to y, when I set it equal to 0, we can get x squared equals 6y minus 3y squared. So I'm going to substitute the x equals 0 into my partial derivative for y. So my x equals 0 from my partial derivative with respect to x equaling 0. Plug that in to my partial derivative with respect to y equaling 0. And when I do that, we get either y equals 0 or y equals 2. So if x is 0, y could be 0, and we'd have the critical point 0, 0, or we have the critical point 0, comma 2. Now my other option that we got from when my partial derivative with respect to x was 0 was that we got y equals 3 halves x. So when I plug this into my partial derivative with respect to y equaling 0, we get x squared equals 6 times 3 halves x minus 3 parentheses 3 halves x quantity squared, which reduces to x squared equals 9x minus 27/4 x squared, which we can solve, and we get x equals 0 or x equals 36 over 31. If x is 0, we can plug this back into my y equals 3 halves x to get y is 0. That's actually a critical point that we already found, so I'm not going to repeat stating it. If x equals 36 over 31, again, I plug that into y equals 3 halves x to get y equals 54 over 31. So we get the critical points of 0, 0, 0, 2, and 36 over 31, comma 54 over 31. So now to determine if these critical points are going to be minimums or maximums or saddle points, we need to get my second partial derivatives. So f sub xx equals 6x minus 2y, f sub xy equals negative 2x, and f sub yy equals 6 minus 6y. If I plug in 0, 0 for my classification equation, my f sub xy squared minus f sub xx times f sub yy, we get that this equals 0. So this means that my change in z could have one solution. So we could have something interesting going on here. We know also that f sub xx equals 0. And this is really a problem because now my second derivative in the x direction is 0. So if we plug in 0 for just y into our function, we get f of x comma 0 equals x cubed. So this shows me that we have a saddle in the x direction. We're going concave down when x is when we're doing negative x from 0, 0, and concave up when we move to the right from the point 0, 0. So even though f sub y equals 6 is positive, and we see that we're a minimum in the y direction, we do actually get a certain kind of saddle point. And after we're done with this, I would recommend that you go ahead and plug in this function into GeoGebra and just take a look at it and see what's going on at the origin if you're having any confusion about how this is working right here. So for the critical point 0, 2, we look at our classification equation f sub xy squared minus f sub xx times f sub yy, and this is going to equal 0 minus negative 4 times negative 6, which equals negative 24. And I'm getting that by just plugging in the 0, 2 into my expressions for f sub xx, f sub xy, and f sub yy respectively. So f sub xx equals negative 4 in this case, and f sub yy equals negative 6 at the point 0, 2. Since the classification equation is negative, that means that we don't have any changes in z, so we must have a minimum or a maximum. And so since f sub xx and f sub yy are both negative, that means that f of 0, 2, which equals 4, when I plug it back in, we get 4 as our output, that's a local maximum. So 4 is the highest z value that we can get near the point 0, 2. Essentially, we have a little hilltop at the point 0, 2, 4. Now my last point, 36 over 31, 54 over 31, we plug that into our classification equation, f sub xy squared minus f sub xx times f sub yy, and we get approximately 20.9. So this is positive. So that tells me right away that it's a saddle point, that we do have changes in z as we go around this point. When I plug in 36 over 31, 54 over 31 into my function, we get that this equals 3.03. So my saddle point is 36 over 31, 54 over 31, 3.03. All right, so yes, like I said, a lot of tediousness in that, but hopefully you're getting the big picture here and are following along. Pause the video, rewatch what you need to, and again, graph this function and take a look at it to see what's happening for yourself. Now the real power that we're going to have here is looking for absolute minimums and maximums. This is going to allow us to do optimization for functions in two variables. So section 12.4, absolute minimum and maximum. Again, with single variable functions, the absolute maximum and absolute minimum of a two variable function are the largest and smallest outputs of the function on its entire domain. So definition 12.4.1, given a function z equals f of x, y with domain D, then z1 is the absolute maximum if z1 is greater than or equal to f of x, y for all points x, y in the domain. z2 is the absolute minimum if z2 is less than or equal to f of x, y for all points x, y in the domain. So in two variable functions, we can have a closed domain with an edge along its border that could potentially contain an absolute maximum or minimum as well. Thus, to find absolute maximums or minimums for a function in two variables with a closed domain, we must look at the critical values inside the closed domain, critical values on the edge of the domain, and the outputs at any corners of the edge of the domain. So there's a lot that's going to go into this that's going to get super tedious. So go slow, pause the video as you need to, really think about what's going on, hash out any extra steps on your own, and email your instructor if you want to ask them any questions about this. So example 12.4.1, find the absolute maximum and absolute minimum of f of x, y equals 3 plus xy minus x minus 2y on the closed triangular region D with the vertices 1, 0, 5, 0, and 1, 4. So the edge of my domain, I want to draw these points out real quick so we can see where we're looking. Actually, this is just going to be first quadrant, so we've got 1, 2, 3, 4, 5. I'm already guessing that I'm going to need to shrink this and move it out of my way. This is going to take up a lot of space, essentially is what I'm saying here. So here's my y-axis. This is going to be my x-axis. We have the point 5, 0. We have the point 1, 0. We have the point 1, 4. And this is a closed region, so we are including the boundary on this. And actually, let me change the color. So, write this out, 1, 0, 5, 0, and 1, 4. This is the equation. This is going to have, this would have a y-intercept of 5, or 0, 5. So this has a nice slope of -1. This line here is y equals negative x plus 5. This line here is y equals 0. And this line is x equals 1. And we're going to need those when we start looking at the edges of this. So let's start with finding the critical points on the inside and determining, and the nice thing here is we actually aren't going to have to classify them as minimums or maximums because we're looking for absolutes, so we can just plug our critical points back into the function and then just see what we get. So we'll be able to cut out some of that work, but still a lot going on here. So I want to find f sub x. This is equal to y minus 1. And we've got f sub y, which equals x minus 2. That's nice. These aren't too bad. So if I set this equal to 0, I get y equals 1. I'll write that out so we can see. So 0 equals y minus 1. We get y equals 1. And 0 equals x minus 2. We get x equals 2. So we have a critical point at 2, 1. And we'll plug this back into the function after we find any other criticals on our boundaries. So if we look now at this function, if we do f of 1, y, so if we're looking on the line x equals 1, then I plug in 1 for x and I get 3 plus y minus 1 minus 2y, and this reduces down to 2 minus y. And so now I think of this as a function in a single variable, and we want to look between, want to say criticals over 0 is less than y is less than 4, because we're looking from this point 1, 0 to the point 1, 4 on the line x equals 1. So we just want criticals between 0 and 4 for y. So my derivative of f of 1, y with respect to y equals -1. And so there's no critical values here. This is just a nice slope of -1 along this line. So we're not going to have any possible absolute maximums or minimums on the line x equals 1. Let's now check, so just x equals 1 line. Now let's look at the y equals 0 line. So we want to see, are there any like peaks or troughs here that could potentially be an absolute maximum or absolute minimum along this line. So if y equals 0, we do f of x, 0. This is going to be nice. This is 3 minus x, and its derivative with respect to x is -1. So again, we're just doing a nice straight line downhill from the point 1, 0 to the point 5, 0. So no possible peaks or troughs along that line. Now let's do, and give myself some more space. If I have y equals -x plus 5, I plug this in for y, so f of x, -x plus 5 is really just a function of x now. This equals 3 plus x times -x plus 5 minus x minus 2 times -x plus 5. And this is going to simplify it down. I've got -x squared. This tells me already I'm going to have a curve, a vertice somewhere. Don't know if it's going to be between the points 1, 4 and 5, 0. And so -x squared, then I've got 5x, and a 2x is 7x. Oh, minus x is 6x. And then we've got 3, and minus 10 is minus 7. And so if I take the derivative then, with respect to x, I get negative 2x plus 6. This equals 0 when x equals negative 6 divided by 2 is negative 2 is 3. So if x equals 3 on this line, then y equals negative 3 plus 5 equals 2. So the point 3 comma 2 is a critical on y equals negative x plus 5 border. So we're going to need to check this in our function to see if we have a max or a min there. And by the way, when I said for the first one that we're just looking for crits over y is between 0 and 4, for the second one we were looking for crits over 1 is less than x is less than 5. I'm not worrying about when x equals 1 or 5 because we're going to have to plug in these points anyways because they might not show up as criticals on any of the boundary lines, but they could potentially still be an absolute maximum or minimum. So for my last line down here, we're looking for crits over 1 is less than x is less than 5. Again, if we're on this line, we're just keeping my x values between 1 and 5. And this point 3, 2 does have an x value between that, so this is definitely something that we need to look at. So to find our absolute maximum or absolute minimum, we want to go through, make sure you can see that there at the bottom, and just plug in all of our critical values. So we've only got 2, so this isn't horrible. F of 2 comma 1, and we get 3 plus 2 minus 2 minus 2. Oops, I wrote x instead of 2. So it's 3 plus 2 minus 2 equals 1. Plug in my other critical value, the critical from the border, f of 3 comma 2. This equals 3 plus 6 minus 3 minus 4, which equals 2. And then we want to plug in the corners of the domain that we're looking at. So f of 1, 0 is going to be 3 plus 0 minus 1 minus 0, which equals 2 again. And then I'll plug in f of 1 comma 4. So here I've got 3 plus 4 minus 1 minus 8. And so I get 7, 6, negative 2. So last corner, f of 5 comma 0. This is going to equal 3 plus 0 minus 5 minus 0 equals negative 2 again. So we have an absolute max of 2 at 3, 2 and 1, 0. So both at this point, 3, 2 is right here. And the point 1, 0. So both here and here we have an absolute maximum. And then we have an absolute, oops, this should be ASB. I'm getting a little dyslexic today. Absolute minimum equals negative 2 at both 1, 4 and 5, 0. So this point that we had, the 2, 1, this could be a local minimum, a local maximum. It could be a saddle point. We don't know, but as far as it goes, it is not the absolute highest, or does not have, when I plug that point into the function, I do not get an absolute maximum or absolute minimum. So that point lies somewhere between the highest and lowest point within this region here. So I don't have a link for it. I'm actually going to just create this graph real quick right now so we can take a look at what's going on. So here we go. I went ahead and plugged in the function, and I gave it some restrictions here if you want to take a look at how I'm setting this up. So I'm doing an if statement. I want to keep my x values between 1 and 5. And to get this little caret symbol, you can probably do special symbols down here. You can also do a double ampersand, so shift 7, to get a second condition, and I want my y values between 0 and negative x plus 5, right? And then we put in the expression 3 plus x times y minus x minus 2y. And we see that we get, here's our domain looking down that we'd drawn before. We get this cool looking little shape here. And sure enough, when we look at it from the right perspective, we see an absolute maximum of 2 at those 2 points, at the point 1, 0, and at that point 3, 2 right here. And at these 2 corners, we get these absolute minimum values, or the absolute minimum value of negative 2. So these two both have the same z value of negative 2. All right, so that's what is happening. Okay. Exercise 12.4.1. So this is same kind of thing, practice for you. Go ahead and give this a shot. See if you can mimic the techniques that I just used in the above example, and I will work through the solution with you in just a few moments. And we're back. So exercise 12.4.1, find the absolute maximum and absolute minimum of f of x comma y equals x cubed minus 3x minus y cubed plus 12y on the closed rectangular region D with vertices negative 2, 3, comma 2, 3, comma 2, negative 2, and negative 2, comma negative 2. So I've drawn out that rectangular region here and see that the boundary lines are given by x equals negative 2, x equals 2, y equals negative 2, and y equals 3. Then I take the partial derivative of my function, so I get f sub x equals 3x squared minus 3. I set this equal to 0. I get 0 equals x squared minus 1, so that x equals plus or minus 1. The partial derivative of f with respect to y equals negative 3y squared plus 12. Setting this equal to 0, I get 0 equals negative y squared plus 4, so y equals plus or minus 2. This together gives us 4 criticals of negative 1 comma negative 2, then negative 1 comma 2, then 1 comma negative 2, and 1 comma 2. So we start by looking at so we then want to look at our boundary line. So inside of this closed domain, we actually have these 4 criticals. I've drawn them as red points on the rectangular region in the xy plane. And then we want to look at the boundary edges to see if there are any criticals on those lines. So if x equals negative 2, I plug that in for x. I get f of negative 2 comma y equals negative 2 minus y cubed plus 12y. I take the derivative of that with respect to y, and I get that equals negative 3y squared plus 12. I set this equal to 0, and I get y equals plus or minus 2. This was actually something that we'd seen above when we looked at the partial derivative of y and set that equal to 0. So same equation and get the same y values. So if we had set x equal to negative 2 and got y equals plus or minus 2, this gives us 2 criticals on the edge of this domain of negative 2 comma negative 2 and negative 2 comma 2. So I've drawn those. Those are actually at the corners here. Oh, I just realized I forgot to do something. I had this forgotten to hit the corners. I'll go over those in a second anyways. So I've got those drawn in. Then I do my boundary when x equals 2, my right boundary to the domain. Plug in 2 into my function f of x comma y. F of 2 comma y equals 2 minus y cubed plus 12. If I had another dyslexic moment, that should be minus 2. There we go. And this again is the same equation that we had a second ago, so y equals plus or minus 2 again. This gives us the critical points on the right boundary of 2 comma negative 2 and 2 comma 2. So I've drawn those in as the red dots on our boundary as well. Now we want the lower boundary to see if there's any criticals there. This occurs when y equals negative 2. Plug negative 2 into my function. I get f of x comma negative 2 equals x cubed minus 3x minus 16. I take the derivative with respect to x, and we get that x equals plus or minus 1. So if y equals negative 2 and x equals plus or minus 1, those are actually points that we already found as criticals of the function overall. So those points are already labeled here and don't need to relabel them. So now we want to check the top boundary when y equals 3. So f of x comma 3 equals x cubed minus 3x plus 9. I take the derivative of that and get 3x squared minus 3. Setting this equal to 0, I get x equals plus or minus 1. So since y was 3, with these x values, we get the critical points on the upper boundary y equals 3 of 1 comma 3 and negative 1 comma 3. Now to determine what my absolute max and absolute min is. I go ahead and take all of these critical points that we found. There are a total of 12 of them, and I plug them all into the function. So I'm just going to go, I'm starting at the bottom left corner and going right, and then going up to the next row of dots and working across and so forth. So f of negative 2 comma negative 2 equals negative 18. F of negative 1 comma negative 2 equals negative 14. F of 1 comma negative 2 equals negative 18. F of 2 comma negative 2 equals negative 14. F of negative 2 comma 2 equals positive 14. F of negative 1 comma 2 equals positive 18. F of 1 comma 2 equals 14. F of 2 comma 2 equals 18. F of negative 1 comma 3 equals 11. F of 1 comma 3 equals 7. F of negative 2 comma 3 equals 7. And f of 2 comma 3 equals 11. So, there's a lot. Finally, we get to write our conclusion. The absolute max is 18, which occurs at the points negative 1 comma 2 and 2 comma 2. The absolute min is negative 18, which occurs at negative 2 comma negative 2 and 1 comma negative 2. All right, that's it. Okay, we've got one more problem. We actually want to bring this to a story problem. Example 12.4.2. Let's go through this, and then this is the end of the lesson for the day. Example 12.4.2. The base of an aquarium with given volume V has a slate bottom and glass sides. If slate costs 5 times as much per unit area as glass, find the dimensions of the aquarium that minimizes the cost of the materials. Okay, so we don't actually have a volume other than just some constant V. So this is a constraint. We know that the volume equals x times y times z, where we should draw this aquarium. We should always draw a picture in story problems, get ourselves figured out. So say x is the width, y is the length, z is the height. Seems like a pretty standard way of setting this up. The volume is going to be the product of those three things. Now what we want to do is minimize the cost of materials. So I need an equation for cost. And it has a slate bottom and glass sides. So we're going to assume that there's no top here. So the cost is going to be, well, we don't know the cost of the glass or the slate individually. So before I say a cost function, I want to say let c equal, little c equal the price per unit area of the glass. So then we know that the slate is going to be 5 times C. So my total cost, let's use capital T so I'm not mixing up capital C's and little c's. So my total cost is going to be, well, okay, the slate is going to have an area of x times y. And so the cost of the slate is 5 times the cost of glass per unit area times the area. So 5c times xy. And c is a constant here, but x and y are variables. So we're going to have 5c times xy. That's just the cost of the bottom. Now the cost of the front and back glass panels here. So the cost of front panel is c times xy. The area is xy, and we multiply that by the cost per unit area. So that's the cost of the front panel. The cost of the back panel is the same, so we'll have 2 of those here. Oops, that should be xz, not xy. Glad I caught that. I'm used to having a classroom of students to catch all of my mistakes. So lastly, we have the cost of the side panels. And that's made of glass, so c times yz. And we have 2 of those again, so 2c times yz. So here is my total cost. And this is a function in 3 variables, and we have not looked at maximizing or minimizing functions in 3 variables. What we want to do is turn this into a function in 2 variables. So the constraint that my volume equals x times y times z, this gives me something that I can isolate and say that z equals the volume divided by x times y. And my volume is some constant, right? That's a given volume. So I can plug this in for z into my cost function to get t as a function of just xy equaling 5c times xy plus 2c times x times v over xy plus 2c times y times v over xy. This simplifies down. 5c times xy plus 2c times v over y. I'm going to rewrite this actually. I'm going to write this as 2cv y to the negative 1 because I'm going to be taking derivatives. And the 2cv is all a constant. Then plus 2cvx to the negative 1. Now I have a function in 2 variables, and we can look at the constraints here. We know that everything has to be greater than 0. So x has to be greater than 0, y has to be greater than 0, and z has to be greater than 0. So any critical points that we're looking for are going to be outside of that. We could also look for criticals when they equal 0, but that's not going to give me an actual aquarium, so we can actually just throw those out the window as well. And just look at our criticals for when x, y, and z are all positive. So I want the derivative of t with respect to x. This is going to give me 5cy. This will be a constant with respect to x, and then minus 2cv x to the negative 2. When I set this equal to 0, the c's will cancel out. I'll show that in a second. 5cy minus 2cv over x squared. And I'll get back to that. I want the partial derivative with respect to y first. This is going to be 5cx, what I say, not what I write, minus 2cvy to the negative 2. When I set this equal to 0, I get 0 equals 5cx minus 2cv over y squared. So I want to find solutions, x and y solutions that satisfy both of these. I'm going to add this to the other side and divide by c. So I get 2v over x squared equals 5y, or, yeah, let's do this. Let's say now that y equals 2v over 5x squared, so that I don't have to do any square roots, and I can now plug this in over in my second equation. So I'll divide the c out and get 0 equals 5x minus 2v over, in parentheses, 2v over 5x squared. And I'll add this to the other side, so I have 2v over 2, let's square it, so it's going to be 4v squared over 25x to the fourth equals 5x. So here we do some reduction. I'm going to get, let's write it like this, 2v over 4v squared times 25x to the fourth equals 5x. And then this is going to reduce to, cancel some 5's here, I'm going to get 5x to the fourth over 2v equals x. I want to subtract so I don't accidentally lose any solutions here. So 5x to the fourth over 2v minus x equals 0. If I divide an x out, then we actually lose the x is 0 solution, which would be fine in this application, but we're going to go ahead and just, for good practice, leave it in for now and then exclude it in a moment. So x times 5x cubed over 2v minus 1 equals 0. So excluding the x is 0 solution, we get 5x cubed equals 2v by adding the 1, then multiplying 2v. So x equals the cube root of 2v over 5. And then I'm going to plug that back in for my y. So I'm going to plug this in now over here to get y equals 2v over 5 times the cube root of 2v over 5 quantity squared. This is going to be fun. So we have 2v over 5 times the cube root of 25 over 4v squared. I really want to do this in exponents instead of roots. So 2v over 5 times 5 to the 2/3 over 2 to the 2/3 times v to the 2/3. I'll flip this up to the top. I'm going to get 2 to the 5/3 times v to the 5/3 over 5 to the 5/3. Or if I put this back into root form now, this is 2v over 5 cube root thereof all to the 5th power. No, I totally made a mistake because I flipped when I shouldn't have. I should have flipped that up to the top. Okay, backing up just a bit here. I'm sure some of you are like, wait, what's going on? Yes, I made a mistake. I am human. I do it. Let's just go back and rehash this real quick. So this is 2v over 5 times, I do want to do exponents here. So this was going to be 5 to the 2/3 over 2v to the 2/3. So I can flip this, but I need to do it on the outside here, not keeping it underneath. Now we do subtraction of exponents. So 2v is to the first, minus 2/3 is 2v to the 1/3 over 5 to the 1/3. This is more the kind of answer that I was expecting. I was thinking that we should be symmetrical with x and y. So we have 2v over 5 cube root thereof. I'm just going to leave it in that form. And now we can take these and remember that z equals v over x times y. So taking these and plugging them in up here, we get z equals v over the cube root of 2v over 5 squared. So I will say that this is v times 5 to the 2/3 over 2v to the 2/3. So we're not going to have quite the same symmetry in the z direction. That's because we have the slate on the bottom. So the sides, we want to keep the slate nice and symmetrical to minimize its cost, but then we want to have the height be a little bit different since the glass is less expensive by a factor of 5. So let's see how that works out in our solution here. So we're going to have v to the 1/3 on top times 5 to the 2/3 over 2 to the 2/3. And I can write this as the cube root of v, let's go 25v over 4. So we do see a little bit of symmetry in these answers, but definitely the z value being bigger than my x and my y values. So here we were multiplying v by 2/5. Here we're multiplying v by 25 over 4 before taking the cube root. So the cost, all of these are positive values, by the way. V is positive, so we are getting positive x, y, and z values. So the cost of the aquarium is minimized when the dimensions are 3 or cube root of 2v over 5 times cube root of 2v over 5 times cube root of 25v over 4. In whatever units the volume is given. And that's it. So that is all we're doing here. We might go back in, well, if we had multiple solutions or if we were concerned in any way that this wasn't going to minimize, we might be able to do a second derivative test with our whole classification that we saw above. But in this case, since this is the only critical point we're getting, it should give us a minimum value. And if we had specific dimensions, we could go ahead and plot this and confirm our answer in that case. But we don't, and we're not going to worry about it now. This has been a long enough video, so thank you everyone for watching. Hopefully you were able to follow along, and I will talk to you in the next lesson. Take care.